Okay, today we are going to talk about sequences and infinite sequences versus finite sequences. This is an example of a sequence. They usually go in these set braces. This is going to be a finite sequence because it has an end, versus this one will be an infinite sequence. Yes, the way you get the next term, etc., is different for both of these. This one goes forever. You can also define one as this. No, not a comma. That should be a colon. So that's essentially a formula for it, and the values for k are natural numbers or positive integers, depending on how you want to look at that. Both mean the same thing. So defining a sequence explicitly. Explicitly means I have a formula that I can just plug in which term it is and get the value. So find the first 6 terms and the 100th term of this sequence. This is example 1. So here's the formula, a sub k equals k squared minus 1. Well, the first 6 terms, so I'm going to plug in 1. And I'm going to label the first term as a sub 1. 1 squared minus 1 is 0. The second term, 2 squared is 4 minus 1 is 3. The third term, 3 squared is 9 minus 1 is 8. Fourth term, 4 squared is 16 minus 1 is 15. Fifth term is 25 minus 1 is 24. Sixth term is 36 minus 1 is 35. It also asks me for the 100th term. The 100th term, 100 squared is one with 4 zeros, so I'm going to double the zeros. So 10,000 minus 1 is 9,999. So that is a explicit definition, meaning I just plug in the term. A recursive definition uses the previous term. So recursive definition can look like this. So what this is saying is my first term is 3, b sub 1. B sub 1 means term 1. My whatever term is b sub n, so that's my nth term. I can use it for the second one first. It means b sub n minus 1 means take the previous term, or the one before it. So if I'm generating a list, and then I'm going to add 2. When I'm looking for b sub 2, I take the term before b sub 2, that's b sub 1, plus 2, and I get 5. Now I want b sub 3, or b3, sometimes we'll call it. b3 minus 1 is b2. That's this one, the one before. 5 plus 2 is 7. Okay? If I want b sub 100, I have to know b sub n, b sub 99. Which this isn't that hard. I'm just counting by 2s. So I could do 99 times 2 plus 3 to get b sub 99. But does that make sense? We have this sequence where it's built off of knowing the previous term. So this is example 2. Okay. Before we talk about Example 3, we need to talk about convergent versus divergent, or converges or diverges. So converges means there's a limit of my sequence. Remember, we've talked about limits in the past, and that's saying, where is it going towards? And a lot of times we had some horizontal asymptotes, and it would be going, we'd talk about our graph, and it would be going towards maybe 12. So this would be what we would say converging, it's a sequence that's converging to 12. And there is a value that the further out I go on my infinite sequence, nope, I misspelled diverges. Diverges means there is no limit to the sequence. And it doesn't mean there's no max or min. It just means it's not getting closer to a certain number. Like this sequence is alternating between 1 and -1. There's no single number it's getting close to. Okay. If it's got 2, it does not converge if there's 2 limits. It really means there's no limit. So we're going to talk about whether these converge or diverge. And if so, what's the limit? So these fractions are all getting a little smaller. I could represent this by 1 over n. And as n gets really large, this goes to 0. So that if it goes to a single value, that converges. Part B of this example, this is going to go to, ultimately, is that 1 doesn't mean a whole lot when we're talking about a million. 1,000,001 divided by 1,000,000 is very close to 1. So it also converges. This one, that just keeps getting bigger and bigger, so that diverges. And our last example, it's kind of the one we already talked about for diverging. That can be represented by -1. Oh, they started with -1. I started with +1. The book starts with -1, so they can do -1 to the n. I need to do -1 to the n plus 1 or -1 so that I have a positive to start with, because -1 to the 1 plus 1 is -1 squared, and that is positive. Okay, so finding limits of a sequence. We've done some of this before with rational functions. So this is the formula for my sequence. And remember, we can kind of use this largest over largest trick. And that's 3. Just reduce 3n over n to 3. Again, largest over largest gives me 5 over n. As n gets really large, that's 5 over a gigantic number, that goes to 0. So if n is large, like a million. 5 over a million is getting close to 0. So any of these that have a 0, these have a limit that is a number. They converge. If they don't have a limit that's a number, again, even though there's a plus n here, because I'm talking about like a million squared is a trillion. Who cares if I add another million? So this goes to n. That diverges. N is not, there's no numbers. N gets larger, it keeps getting larger. Okay, now we're going to talk about arithmetic versus geometric sequences. Arithmetic means we're adding the same thing. Arithmetic is kind of like arithmetic. And my general formula for this, here's the recursive version. A sub 1 equals something, and we call what we're adding each time the common difference, so D. The explicit formula, the recursive is always going to have the two parts. You have to define A sub 1. The explicit does not, and it does not in any way reference the bottom one. So this is explicit. We've also got geometric, which geometric sequences are I multiply the same by the same thing every time. I like to use G sub 1 for G. The books keeps using A. So we have a first value. I don't know what it is. And in this time, I multiply. We call it R for the common ratio, or what I'm multiplying by each time. So maybe I'm multiplying by 2. I'm doubling every time. Or I'm multiplying by half. No, there should not be an or equal on that. Its explicit formula for geometric is G sub 1 R to the power of n minus 1. So we're using an exponent here for the explicit formula. So for each of the following sequences, find the common difference, the 10th term, a recursive rule, and an explicit rule. So this is going to be example 5, and this is going to be arithmetic ones. A, -6, -2, 2, 6, 10. So that's adding 4 each time. The 10th term, well, I'm going to find the formulas first. A sub 1, so I'm going to do part C and part D. This is part 1 of example 5. A sub 1 is -6. A sub n is previous term. Why am I doing +1? Previous term +4. You always add this for n is greater than 1 because you can't do the first term that way. The explicit formula, A sub n equals first term +4 n minus 1. Sometimes you'll see them simplify this as -6 plus 4n minus 4 by distributing, and then that equals -6 or -10 plus 4 and or 4n minus 10. they want the 10th term. I'm just going to plug into this formula. I could do any, but 4n is 4 times 10. Let's see why I wanted the explicit formula first. 40 minus 10 is 30. Very quick and easy to do the explicit formula. The second sequence, not quite as easy. Oh, I forgot to actually write down. First common difference is 4. So here's my sequence for the second one. And so my common difference is, to find a common difference, I can just take them and subtract. There's a little trick here, though. With this minus, the laws of logs say that's division. My common difference is ln2. So if I'm looking at here, ln3 plus ln2, that's ln3 times 2, which is ln6. So we'll do part C. A sub 1 equals ln3. A sub n equals ln, no, the previous term. I'm getting ahead of myself into recursive formula or explicit formulas. My explicit formula then is ln3 plus common difference times n minus 1. I'm not going to try to simplify that one. Now I want the 10th term. I'll call that a sub 10. No, I don't need two equal signs. That's got to be a plus. 10 minus 1 is 9. I would often write this as ln3 plus 9 ln2. ln2 to the ninth. 2 to the ninth is 512. So ln3 times 512, which is ln of 1,536. Okay, so that is example 5. Those are arithmetic. Now we'll do some geometric, which is going to be example 6. And it asks me for the same things. So my first sequence, no, not that. That'd be arithmetic, adding 3. This one is going to be doubling every time. Common ratio is 2. We'll get the 10th term later. Explicit formula, or the recursive formula, 2 times the previous term. My explicit formula, plug it in my form. First term Ratio is 2 to the n minus 1. My 10th term ten minus 1 is 9. 2 to the ninth again is 512. Times 3 is 1536. My second sequence here is going to be this. So notice I'm raising the exponents by 2, which using exponent rules means finding my common ratio, that's multiplying by 10 squared, or multiplying by 100. So I could think of it as 10 to the negative 1 is 0.1. 10. So I've moved the decimal 2 places, that's multiplying by 100. My recursive formula starts with my first term, 10 to the negative third. Take my ratio, 10 squared or 100, times the previous term. My my explicit formula, G sub n equals this time I'm just going to write 100. And finally, I've got to get the 10th term, which is G sub 10. Ten minus 1 is 9. 100 to the ninth. I have 18s. Actually, I probably should probably just do this with the exponents. That's 10 to the 18th times 10 to the negative third. I add those exponents. I multiply the exponents 10 squared to the ninth, multiply the exponents 10 to the 18th, and then 10 to the 15th is the 10th term. Okay, so constructing sequences. The second and fifth terms of a sequence are 3 and 24 respectively. Find the recursive formulas for the sequence if it's arithmetic, if it's geometric. So here I know that for part A here, a sub 2 equals 3, a sub 5 equals 24. And we know this is arithmetic, which means a sub 3 equals 3 plus r, and a sub 4 equals 3 plus r again, so 2r. And a sub 5 equals 3 plus 3r, which, hey, that's 24. Oh, it shouldn't be r, this should be d. This is arithmetic. Common difference. What am I adding each time? So now I can just solve this. 21 equals 3d. D equals 7. I'm asked to write the recursive formula. Now I do need to actually go back to a sub 1, which should be 7 less than 3. So that's negative 4. And then I'm just adding 7 to the previous term. So that was part A. This is example 7. Example 8 No, part B of example 7 asks to do the same thing with geometric. So G sub 2 equals 3 and G sub 5 equals 24. G sub 3 then is 3 times my ratio. G sub 4 is my previous one times my ratio, or 3r squared. G sub 5, 3r squared times the ratio again, 3r cubed. So I'll divide by 3 and I'll get 8 equals r cubed. R equals, this one's got to be positive too. It could sometimes be a plus or minus. It could sometimes be a negative. This one was not that case. So I know I had to multiply by 2 to get to 3. That means so my first term is 3 over 2. So when I write my recursive formula, I have to have that. Okay, let's talk about how to do sequences on the calculator. I've already got this one graphed, but there is a sequence mode on your calculator. If you press the mode button down here, function, parametric, polar, SEQ is sequence. Could also be, if you're on the older 84s, it's func, par, pol, SEQ. You want to select sequence. Now when I go to y equals, everything looks a little different. Okay? And we're just going to enter this u sub n line. You could enter your sequence with a few numbers, but u sub n, the sequence I'm trying to enter is a sub k equals k squared minus 1. Well, your calculator does not have a k button, but the variable button has an n. Notice that starts with function with x, t for parametric, theta for polar, and n for sequence. So now that I've entered that, I'll go to my window. It tells me it wants me to start at 1 and go to 10. Okay. 10 squared minus 1 is 99. So I've got my n min at 1, my n max at 10. My plot starts at 1 and it steps by 1 each time. Those are kind of my defaults. My x's, I went from 0 to 10 because x is functionally n. My y's, I went from negative 10, so I had a little more 0, to 100 because that's just over 99. And then I can hit graph, and here's my graph. If I want to look at the numbers, I can hit second graph, and I can hit table. We don't usually have a 0, but here's all the numbers for you. And it just kind of keeps going. Okay, so these are the numbers of my sequence generated by the calculator. Okay, so using a graphing calculator to generate it for specific terms, well, if I know my formula, that was example 8. Example 9, we're going to skip over. If you know the formula, you just enter it. Okay. And I would just do it this way and use the table. If you don't know the formula, there are different ways that you can do it. Okay. So I'm going to go to a calculator's window. I'll clear all of this. And I'm going to skip rid of that too. So my first sequence here is, here's the recursive definition. A sub 1 equals -2. A sub n equals a sub n minus 1 plus 3. So we can store things in a couple of different ways. So one of the beautiful things about the calculator is it can use previous answer. So if I just do -2 here, that was my first one, -2, and then I just hit plus, it'll use the previous answer, and it'll just keep adding the sequence. Okay. I also want to talk briefly about the most famous recursive defined sequence, which is the Fibonacci sequence, which adds the previous two terms. Oops, didn't mean to draw that, but so the Fibonacci sequence, I'll write out the terms here in a second, but you need to define the first two terms because it's going to add the previous two. This time I need to be n greater than 2, so I have that. So this sequence, 1, 1, then add the previous term, a sub n minus 1, plus two terms ago, a sub n minus 2. So 1 plus 1 is 2. Now I've got 2 plus 1 is 3. 3 plus 2 is 5. 5 plus 3 is 8. 13, 21, 34, 55, 89. And that is the Fibonacci sequence, spelled like this, named after a famous Italian guy. Okay, that is it for section 9.4.